This is Standa from the Brno Mars Rover team, and I am pleased that today I can finally introduce our competition rover to you. The rover for the ERC 2025 is called Freya. 17 of us, students from Brno University of Technology, have been working tirelessly to design, build and test every component needed to meet competition challenges. Our team consists mainly of electrical engineering, mechanical engineering and computer science students. We have a strong background in robotics, control and sensor processing, which we believe has greatly helped us in designing a system that is both performant and extensible. Our team is divided into several sub-teams, each responsible for a specific part of the final system. Since the rover platform is entirely new, most of our members have been focused on designing, manufacturing, assembling, and testing the chassis. This sub-team, led by Martin Mainisch, is also responsible for developing the manipulator arm that will be mounted on the chassis. All of the electrical components, printed circuit boards, motors, their drivers, and wiring are managed by our electronics sub-team, which is led by Adam Legowski. Software team, which is led by Miloš Cihlar, is creating all of the software needed for the chassis, its autonomy, communication with the base station, and the operator's graphical interface. Miloš also leads the team that constructs, programs, and tests the accompanying drone. The drilling submodule is developed as a standalone device capable of working independently. The team that develops it is led by Willem Strakon. As most of us are science and space enthusiasts, science planning is a cooperative effort. Procurement and public relations are currently done by me and Miloš. Throughout our studies, we dreamed of taking part in a complex robotics competition, one that would challenge us to form a multidisciplinary team and manage a long-term project from the ground up. That dream became a reality in late 2023, when we officially founded the Brno Mars Rover team. In designing our rover, we drew inspiration from proven suspension systems used on other celestial bodies. The one that stood out to us the most was the rocker bogie system. Sure, having 6 wheels adds complexity, but the improved terrain handling and, let's be honest, the stunning look of the design won us over. The chassis and suspension are built from off-the-shelf aluminum extrusions. These provide excellent stiffness while allowing for rapid prototyping and easy adjustments. For non-critical components, where the mechanical stress is minimal, we use 3D printing as our go-to manufacturing method. It's affordable, fast, and even suitable for functional parts. When testing reveals excessive wear or flexing, we replace those parts with CNC milled aluminum for improved durability. All of the rover's wheels are 3D printed using flexible TPO filament, which allows them to adapt to uneven terrain and maximize surface contact for improved traction. Each wheel contains an integrated DC motor, enabling independent control for precise movement. Additionally, the corner assemblies can pivot, allowing for efficient turning, even enabling zero-radius maneuvers. The rover is powered by a 40-volt lithium-ion battery pack, equipped with an integrated battery management system that allows for convenient charging directly inside the rover. When time is limited, the battery can be quickly removed and swapped for a fully charged one, ensuring minimal downtime. At the heart of the electrical system is our custom-designed power distribution board, which includes switched power supplies to deliver 24, 15, 12, and 5-volt levels to the various subsystems. Each voltage rail is individually monitored for anomalies and can be rapidly shut down to protect sensitive and expensive electronics. All of the rover's internal components are accessible through a hinged door located on top of the chassis. Opening it provides easy access to connectors, wiring, and all key hardware elements. At the core of the system are a Nuke Mini PC and a Raspberry Pi, which together serve as the rover's brain. Both run Linux and are built on the Rust 2 framework, which forms the foundation of our entire software solution. Before testing on real hardware, we almost always simulate the mission first, primarily using Gazebo. For navigation on the Mars Yard, we utilize components of the Navigation 2 framework, alongside our custom 3D traversability map layer. The method relies on elevation maps generated from 3D point clouds obtained via LiDAR or depth cameras. Traversability is determined by computing the normals of the estimated surface. The rover is capable of autonomously planning its trajectory and assessing whether a given path is traversable. For sensing, we use a combination of LiDARs and cameras. Pose estimation is achieved by fusing data from the IMU wheel odometry and either visual or LiDAR-based odometry. For more advanced and staged missions, we designed the rover's behavior using a behavior tree-based approach. To extend our rover's capabilities into the air, we've developed an autonomous quadcopter companion, built on the reliable F450 frame and powered by a Pixhawk flight controller running PX4 firmware. It supports vertical takeoff, omnidirectional movement, precise landings, and fully autonomous emergency descent. The drone is controlled off-board by an NVIDIA Jetson Orin NX with 16 GB of RAM, which communicates with the flight controller using the Mavlink protocol. Its control software runs on ROS2, integrating seamlessly with the rest of our robotic system and allowing for coordinated ground-air operations. The platform is designed for autonomous missions with a strong focus on repeatability and robustness. It is powered by a 4S lithium-ion battery pack, providing flight times of up to 20 minutes. A downward-facing camera is used to detect competition probes and locate the landing marker. To ensure precise landings, a downward-facing 2D LiDAR measures the drone's altitude during descent, enabling smooth and consistent touchdowns. In the event of an onboard computer failure, the Pixhawk firmware automatically takes control and initiates a safe landing at the current location. This failsafe also activates in cases of low battery or signal loss. All emergency procedures have been thoroughly tested in both simulations and real-world flight trials. We are developing both the manipulator arm and the deep sampling device as standalone modules capable of independent movement without being connected to the rover. This approach allows for rapid prototyping as well as software development and testing independently of the chassis progress. The first version of the manipulator arm served as a testbed for software development. We created a graphical user interface that enables control in the end effector coordinate space and leveraged a RealSense camera to lock onto and position itself automatically in front of predefined targets. We are currently designing and assembling a new version of the manipulator arm that is better suited for mounting on the rover. This version is built to provide 6 degrees of freedom, a reach of 50 centimeters, and a maximum payload capacity of 1 kilogram. The deep sampling device is based on a geared-down DC motor driving a spiral drill housed within a PVC pipe. It is lowered into the ground using 2 linear rails with lead screws. Beneath the drill, a sample collection mechanism can position any of the 4 collection cups to contain the sample for weighing and further analysis. Finally, in addition to preparing for the competition, our team members proudly share their work with the public. They take part in social events, university open door days, and showcase their skills during official university visits. They also strive to pass on their knowledge to future university students as a way of giving back the support we've received from our university.